We're now going to shift our attention to dielectrics, or insulators. And so what we're going to consider in this video is polarization in dielectrics. So dielectrics are not going to have the same amount of free charge carriers, or really any free charge carriers, the same way that a metal does. However, we want to keep in mind that these electrons are not bound such that we can't ever move or break them away. Of course, if we apply a strong enough force, we could break electrons out of that dielectric sort of lattice. And if we apply some finite force, even if it's not enough to break the electrons away, we can definitely see some small displacement from the original position. And so to see sort of a basic example of that, let's consider sort of a really simple atomic model. And so in general for our atomic model, we're going to have some nucleus in the middle, which is going to have a positive charge. And then around the outside, we'll have some electron cloud. And I'm just going to really, crudely draw some electrons around that to indicate that we have negative charge distributed evenly around the positive nucleus. And so if we don't have any applied electric field, of course, it's just going to look like that. Now, what happens if we take that same atom and now we apply an electric field? So we have some electric field in this direction from left to right. Well, of course, what's going to happen is our electrons are going to experience a force in the opposite direction of E, so from right to left, and our nucleus is going to experience a force in the direction of E, from left to right. And so what happens is our circle will sort of get elongated and it'll look more like an egg shape. And so we'll have our nucleus sort of displaced a little bit to the right, and we'll have our negative charge sort of displaced over here more towards the left. And so what we can do is we can model this as sort of being equivalent to that initial configuration. So let me just copy this initial configuration to make things easier. So this initial configuration plus a dipole. So we can say it's equivalent to that initial configuration, and then we have our dipole, which is going to have a negative and a positive charge. So we can call this our Q, this is our minus Q, and our plus Q. And remember, we said this distance between is magnitude D, and it's a vector which is directed from negative to positive. And so let me clean that up a little bit. Let's make that D a little more legible. And so, of course, as we talked about in the last unit, whenever we're dealing with a dipole, we can characterize that with something called a dipole moment. So our dipole moment is given by P, which is a vector quantity. So Q, which is the magnitude of the charge, so both positive and negative have the same magnitude, and then multiplied by that distance vector D. Okay, so this is only for one atom. Of course, a dielectric material is going to be many, many atoms constructed together in some type of lattice. So what we can say then is, what if we have n dipoles in some differential volume? So n dipoles in some differential volume delta V. All right, so, and this is of course still in our dielectric. So let's write that just to be clear. So we can talk about then our total dipole moment, which is just going to be the sum of all the individual dipole moments. So our total dipole moment due to our electric field is just going to be Q1 times D1, so that's our dipole moment for our first dipole, or we could think of it as our first atom, plus Q2 times D2, so our dipole moment for the second one, so on and so forth, all the way up to our nth dipole, which has Q times D N. All right, and so we can just represent that as a summation, of course, so we can say this is a summation from K equals 1 to N of our charge Q sub K times our vector D sub K. So with that information, we can then go on and define something called polarization. So our polarization, P, so capital P for polarization, is just a measure of the intensity of our polarization in that dielectric material. So it's kind of confusing because the parameter is called polarization and it's a measure of intensity of polarization. So hopefully from the context it can be clear which one we're talking about at any given time. So polarization P is a measure of the intensity of the polarization in the dielectric. And so what that is given as is P is just equal to the limit as that differential volume delta V is going to 0 of the sum of our dipole moments divided by delta V. So we have sum from K equals 1 to capital N of our Q sub K times D sub K, and we're just dividing by our delta V. So that's our definition of polarization in a dielectric material. Now, we have a couple different types of polarization, or rather a couple different types of material. So the first one is going to be a nonpolar dielectric. So nonpolar dielectric. And so what this is there's no dipoles until Re is applied. In other words, basically there's no separation of charge, everything is nice and evenly balanced. So no dipoles before application of E. But then once we apply that E, so our E field is going to create these dipole moments which are going to align with the direction of E. So E creates dipole moments that align with E. And so by align with E, we mean that they're going to be parallel, the same way we can see that this dipole moment is parallel with our electric field that was applied in this simple case. So nonpolar dielectrics is one type. The second type are polar dielectrics. And so in this case, there are actually already dipoles present in the molecule or in the structure before application of an E field. So polar dielectric is basically our molecule, typically it'll be a molecule, has dipoles. And so let me write our technical term here. So technically they're called permanent dipoles because again, they're going to be there before we even apply an electric field. So permanent dipoles, and let's just say present before our E application. But once we do apply that E, then our dipole moment is going to be parallel to E, the same way that we saw with this simple case up here. So these permanent dipoles, which are present before the E application, are also going to be randomly oriented. So for instance, maybe we have something like this, and let me make that a little bigger so I can fit my sign in there. So we have some dipoles, maybe they're something like this. Just a few of these as an example. So we would have maybe some dipoles like this, and so one example of a polar dielectric would be water. So H2O molecules have permanent dipoles. And so if we apply an electric field, what would happen is we would have an E field in this direction, and of course our positive charges are going to move to this end and our negative towards this end, and all of our dipoles will align in that manner. So that's the difference between our polar and nonpolar dielectrics. So we can talk about sort of one more important thing here, and this is going to be the charge in the surface, the charge on the surface I should say, and the charge on the volume for these polarized dielectrics. And so we're not going to go through all the details of doing that, but if you want to see the details, you can look on pages 188 and 189 in the textbook. And the starting point for this is basically our voltage equation for dipoles. So voltage equation for dipoles ends up giving us two quantities. And so I'm going to define these in a little more detail here in a little bit, but we have rho sub PS, which is equal to P dot UN, and we have rho sub PV, which is equal to negative del dot P. All right. And so our rho sub ps is our bound surface charge density, or sometimes we'll call it our polarization surface charge density. So this is our bound, or sometimes we'll say polarization charge density. And that unit vector u sub n is just an outward normal vector to the surface. So our u sub n is outward normal vector to our surface. All right, and then for our rho sub PV, that's just going to be our bound or polarization volume charge density. And so when I'm saying that these are bound or polarization charge densities, that's as opposed to free charge density in the volume or the surface, as we've seen in previous chapters or as we've talked about with metal. So in a metal, the charge can move around, and if it's a perfect metal, all of the charge will go to the surface. In this case, if we apply an electric field to a dielectric, it's going to create these dipole moments. So we will have some polarization due to that, and we will have some corresponding bound charge density both on the surface and in the volume. But the key thing is that that charge isn't moving, so it's sort of fixed in place. So again, that's why we say it's bound, sort of as opposed to free, like we have in the case of a metal. So one last thing we're going to talk about, just to sort of set up for our next video, is we can say if our dielectric is initially neutral, then it's going to stay neutral after being polarized. So if our dielectric is initially neutral, and we have, basically we're saying no free charge is added, then it's going to remain neutral after polarization. And I think all of these ideas about our bound surface charge, and once we talk about our free charge here in a little bit in the next video, are going to make a lot more sense once we get into some examples. All right, and so basically just to write what this is sort of in terms of an equation, we're saying that our integration of all of our bound surface charge, so that rho sub ps ds, plus the integration over our volume of all of our bound volume charge in that dielectric material has to be equal to 0 if we have no free charge added. And so that's going to be true after polarization in a dielectric. And so that's our total charge of the system.